Let's look at some observational evidence of the distribution of potential verticity and then come back and try to explain it in terms of the physics. Okay, so we looked at the PVS, or the potential verticity substance, integrated around a latitude line. We are going to look at the characteristics of the PV fields on 370K isentrope, which is in the upper atmosphere, which is our main focus here. This is the January climatology, which means it's averaged over a long time, and this is how average January would look like. And then this is a particular day, 19 January 2001. It says 2012 down here, it says 2001 here, Peter. Okay. So in the climatology, you see what we had seen before. Coming off of the East Asian continent, there is the strong potential verticity that is associated with the westerly jet. And then you have the exit of the westerly jet, this intrusion into the westerly duct, and then you have a similar intrusion down here in the Atlantic as well, and you have our easterlies shown here as the zero line of the zonal velocity. And we will look typically at these two latitudes just to see how the equatorward and poleward migrations of the PV occur. So that's the 30 north latitude line. This is the 10 north latitude line. The other characteristics, we know already that the sign of the PV is different across the equator. So here it's negative, and we won't focus much on the characteristics here, although you can see in the westerly duct there's an intrusion from this side as well. You can look at the transport of PV on 370K across the 30-degree north line and the 10-degree north line here. They are in the potential verticity substance units that we have just defined. And when it is positive, it is northward, so they are shown in this yellow line. When it's negative across 30 north and southward across the 30 north line, it's in this thick red line. So you can see that there is the Pacific and the Atlantic intrusions of the PVS, I will just call it PVS, across the 30 north line. And there are other regions where there is northward transport across the 30 north line. And the main point we will note again and again is that if you just integrate across this, that's approximately equal to zero. So the southward PVS is being compensated by the northward PVS. Similar thing also works at 10 north, but we will see that we will mostly focus on the 30 north and look at the physics anyways. But in general, if you look in the northern hemisphere, at both latitude lines, there is a smaller cross latitudinal transport here than here, because it's the strong gradient up here. But you can see similar ideas that if you integrate across, you will get close to zero net PVS transport across latitudinal lines. If you look at a particular day, you get a much more interesting picture. This is in the winter month. The jet stream is pretty strong in the northern hemisphere. Winter hemisphere, remember, Hadley cell moves, the thermal wind, vertical shear, westerly jet are all strong. But now on a particular day, you see much more of a feature in the intrusion of the PVS. You can see a clear invasion down into the low latitudes, and then they're being advected westward by the easterly winds that are down here. And it's broken into pieces, into filaments and eddies and so on, with some minima here that we will come back to again in the summer months. So This then migrates back into the high latitudes. This is the main point of this chapter. This tropical extratropical interaction is about PVS coming in and then PVS going out, and there are reversible Rossby wave propagation, and then there are irreversible processes where Rossby waves break down and then the PVS is dissipated here. And we will see that this dissipation is going to be critical for maintaining the zonal flow in the deep tropics in the upper level. So this is what we are looking at. Strong jet, exit region, upper trough, westerly duct, the seasonality of it, and the interaction with the extratropics, and then PVS going back into the extratropics. Do the same thing for July at 370K. Boreal summer month, you again see the upper tropical trough this time instead of the westerly duct, which is a summer feature. You can see the changes here, which are really interesting, both on a given day and in the climatology of July. You have a minimum in PBU, potential vorticity, because of the monsoonal heating and the monsoonal circulation. So you still have upper tropical trough pumping in PBS, being advected westward, and then heading back towards the high latitudes, but around this Tibetan plateau and the anticyclone that sits here during the monsoon season. And that's obvious also on July 9th of July in 2001. Again, it says 2012 here, but 2001 here, it doesn't matter. Typically that's what you would get, but again you will see the breakdown of this PVS into filaments and eddies and so on. And the story of cross-latitudinal transport again is that the southward transport is approximately equal to the northward transport. So if you integrate across the latitudinal band, you have net zero transport across these latitudinal bands. Again, a smaller potential vorticity substance transport across 10 knot, but still net zero, close to net zero. Okay, this is what we have to explain. This is observed physics. This is to remind us of the vertical structure we are looking at and why we picked 370, which is up here. We will also see an example of 330, which is down here, but we will see that if you look at January, on 330, there are similar features, but not as obvious. You'll still see some southward penetration between these two latitudinal bands, smaller penetration at 330K at both latitudes, especially at 10 knot. It's fairly small, but again, integrated across, it's close to zero. We don't show this for January because the 330K isentrope intersects the Himalayas and the Tibetan Plateau during the July season because of the monsoon. Okay, so this is what we have to explain from physics. But the main point you must remember is that the tropical extratropical exchanges seem to have this loop of PVS coming in to the tropics through this westerly ducts and the upper tropospheric trough, and then being advected westward and then being moved back north. So across latitude there is net zero transport of the PBS, the potential vorticity substance. This potential vorticity substance is defined, as we will see, because we can now go to a more general equation, including diabatic heating and dissipation term, and get an equation that's valid everywhere without any restrictions, and then see that it is still conserved. And that's where the impermeability theorem comes in, that we will look at in the next podcast. Okay.